Hey everyone! By now, I feel like you are very comfortable with the idea that it was J.J. Thomson that is given credit for the discovery of the electron. In 1897, he did an experiment with cathode ray tubes, but it's not just the discovery of the electron. He was also able to look at what were some of the physical properties of this new subatomic particle. And when you take a look at properties of a particle, what are the two things that come to mind right away with the electron? The charge and the mass. Now, he wasn't actually able, he's not usually given credit for giving us that very accurate measurement of the charge of the electron. Credit for that goes to Robert Millikan in 1911. But J.J. Thomson and his team were able to work through and get a pretty good value for the charge to mass ratio of an electron. So it's charge divided by its mass. And here's how they did it. And this is something you can follow. In fact, we're going to do an experiment that beautifully illustrates this. So follow along with the math. I recommend that you write this down as we go. I wrote it down first so it would look nice. Just like everything else in physics. I'm going to start with, so just like everything else in physics, what do? We can take a look at the sum of the forces causes the mass to accelerate, and we can look at the conservation of energy. Let's see how we could do that. I'm going to start over on the right-hand side, actually, in my derivation. And if we take a look at conservation of energy, I can say that the electric potential energy is converted into kinetic energy. I'm leaving the signs out of it for now. I think you got this. Now, QV, or Q delta V, would be equal to 1/2 mv squared. But the problem is, even if I could measure the velocity of that electron, which is going really fast inside a tube, I don't know the charge or the mass, so I can't really get any farther in the calculation. Now, I also know that that charge is going to experience a force when it's placed in a magnetic field. So the sum of the forces is going to cause the mass to go in a circle, because that force is perpendicular to the velocity. So if I substitute in QVB causes the mass to go in a circle, I do a little algebra, and I'm right back where I started, which is I have two unknowns in both of my equations. However, when I have two equations and two unknowns, you know what I have? Systems of equations, and I could solve it a few different ways. There's no arguing that. What would be a really hard thing to measure would be the actual velocity of the electron. So if I can get that out of the equation, the other values I may be able to get an experimental value for in a properly designed experiment. And that's what they did. So if we take a look, and this is difficult how I'm going kind of simultaneously, if I look over on the force side, I'm going to have QB equals mv over rc. Now, to solve that equation and get V all alone, I end up with Q, the charge, times B, the magnetic field strength that the cathode ray tube is placed in, right? The radius of curvature, RC, which is if we can measure how much that electron curves in the magnetic field, and we have the mass of the electron divided by the mass of the electron equals V. Good. If I look over on my conservation of energy side over here, if I have Q delta V, now the initial voltage is 0, so I left it as just V. QV equals 1/2 m little v squared. Solve it up for V squared, boom, you're already ahead of me. You get 2Q accelerating voltage all divided by the mass equals V squared. Yeah, algebra. Now, I take over on the forces side, I square everything up. Over on the energy side, it's already solved for V squared. And I have two things equal to V squared. Boom, set them equal. Now, at this point, you're probably thinking, huh? How's this giving me charge to mass? wait. Just wait for it. You'll see it. So now, once I square the left-hand side of that equation, I get q squared, b squared, rc squared, all divided by mass squared equals 2qv over m. And you see it in my work. One of the q's and one of the masses cancel out. Now, I rewrote that over m times b squared times rc squared equals 2v. Yes, I brought the m over. Algebra says that's legal. Relax. Now, my final step is to get the charge to mass ratio of the electron all alone. And I get q divided by m equals 2 times the accelerating voltage divided by the magnetic field strength squared times the radius of curvature squared. And that voltage I can know. The B field I can measure. And RC I can measure. And if I can design an experiment to control the path of an electron and measure these three values and do it consistently, I can find the charge to mass ratio of the electron. Then when Millikan or others had come along and measured the charge of the electron, then we'd also have the mass of the electron. That's mind-blowing, really. What's mind-blowing is we're going to do an experiment in class and do that. So, just to back up from my notes a little bit, to make sure everybody's clear, now, 120-something years later, we do have very accurate values for the charge and the mass of an electron, the mass of that electron at rest. I used some rounded numbers here of 1.6 times 10 to the minus 19 coulombs. The mass is approximately 9.11 times 10 to the minus 31 kilograms, which gives us a rough accepted value of 1.76 times 10 to the 11th coulombs per kilogram. Now, so when we talk about cathode ray tubes, I've generally been drawing them like this, where we have our accelerating potential located in the back. And then we have our deflection plates located inside the back part. You could see an example of that here. And then the electron beam actually travels through that tube and strikes the screen. And when the electron strikes that screen, it emits light, and we can see where it's hit. But instead of utilizing that one today, I'd like to take a look at another setup where we can look at the charge to mass ratio in a slightly different way. So here is our Helmholtz Coil apparatus that we can utilize to measure the charge to mass ratio of an electron. This is a beautiful piece of equipment that actually Winnacunnet has because of my mentor and former teacher, Bob Devantry, when he won the New Hampshire Science Teacher of the Year Award back in the late 90s, was able to put some of that money towards buying us some of this equipment. And we still use it today. So thank you, Bob. Now, taking a look at this, what we have is a partially evacuated chamber filled with some argon gas. That way, as the electrons are traveling in that chamber, we can actually see their path as they collide with the argon gas and photons are emitted. We have our Helmholtz coils, 1 and 2, and I think you guys can notice that the radius of this coil is equal to the distance between them. That allows us to utilize the Helmholtz coil formula so we can carefully measure what the magnetic field is in between these two. Now, because of the path of the electron, I know that that field is actually going to point from the rear to the front. The B field is going to point in this direction. Now, how do we change the strength of that B field? I utilize my DC power supply right here, and this provides current to the coils, and this can be easily changed and recorded using my multimeter. Over on the other side, we have our high voltage power supply, and this can actually go all the way up to 500 volts, but we are going to vary it between about 180 and 300 volts. We have our multimeter that'll measure what that accelerating voltage is. And the other wire that we have hooked up is to just a 6-volt power supply down here, which is hooked up to the heater, which is connected to the cathode on the back, that wire, that the electrons are jumping off of. So we can measure the accelerating voltage. We can measure the strength of the magnetic field. So the only thing left to measure would be the radius of curvature of the electron. Now, how we're going to do that once we get this electron moving is on the back here, there's actually a scale. It's a ruler, and it's actually mirrored. It's very cool because you have to be aware. You don't want to get parallax. Topic for another day. You got to make sure everything's lined up accurately if you're going to measure that radius correctly. So it's a mirrored ruler. So you look at the reflection of your eyeball and the path of the electron and measure the values off of the back of that. All right, I'm going to get my production team to shut the... Oh, wait. They didn't show up to work today. I got to go shut off the lights. Let's see if we can get this thing working. All right, so here's take 2 of trying to see the radius of curvature of the electron when it's going in a Helmholtz coil, thus allowing us to find the charge to mass ratio of an electron. Right now I have my accelerating potential. It's creeped back up to 318. Let's get that down to 300. And if it was dark in here, we would be able to see a nice green beam of light across the electron gun. I'm going to go hit the lights and see if we are in fact able to see that. All right, so if I'm looking at my monitor, I can see a faint glow, but what I would like to do is to maybe disconnect this camera. So I'm going to disconnect the camera and bring it closer to our setup so that in fact we're looking at it right there. And I think you can see a faint green glow down near the bottom. It looks a little bluish on my screen. Hopefully you can see that that is deflecting. So we're not looking at the reflection right now, not those numbers in the back, but down below that, until finally, hopefully, we can get it to snap in to a nice circular path. Can you see that? Here I've decreased the current. Hopefully you are able to see that faint green glow. Now the thing is, I can see it really well with the naked eye, but it's hard to see on the camera. So hopefully you can see that beam changing. Ooh, as I pull away, now I'm going to go back onto the tripod so you can get a relative sense. I can see the greenish glow on my monitor, but I'm not sure you're going to see that clearly. I'm going to go ahead and turn the lights on so that you kind of have a sense of where this close-up is in relation to everything else. All right, so that circular path right there. And travel in a uniform circular path. Now, the stronger I make the current, the stronger the B field, the tighter that radius. Now I'm making the current less, the B field is becoming weaker, and the radius increases. I hope that you're able to see that. Now, with everything aligned perfectly, we should be able to measure simultaneously the current in the coils, thus finding B. We know our accelerating voltage, V, and we can measure the radius of curvature of the path of the electrons as they travel in that circle. And with all that said and done, we can plug into the formula we just derived, 2V over V squared RC squared, and solve for the charge to mass ratio of a subatomic particle, the electron. That's what we're